Greetings, respected judges. We are Team Test Rank from AICHU VIT, and today we present our project on direct air capture, an emerging solution to the growing challenge of rising atmospheric carbon dioxide. CO2 levels have now exceeded 420 ppm, playing a major role in global warming and climate change. While most carbon capture technologies focus on emissions from factories and power plants, they do little to address the large amount of CO2 already dispersed in the atmosphere. This is where direct air capture becomes important, as it enables the removal of carbon dioxide. Our approach explores a simpler and more sustainable alternative. We use tannic acid, a naturally occurring compound found in plants like tea and tree bark, and combine it with iron ions to form a porous metal polyphenol network. This creates a surface rich in oxygen groups and metal sites that can interact strongly with CO2 molecules. To make the system practical for airflow, we coat this material onto activated carbon pellets, creating a packed bed that allows air to pass easily while maximizing gas solid contact. As air flows through CO2, is selectively captured on the surface. When the material becomes saturated, a gentle heating releases the captured CO2, allowing the sorbent to be reused. Now, what makes this approach exciting is its low cost, bio-derived chemistry, and scalable design, offering a promising pathway towards more accessible direct air capture technologies.
Now, I'll briefly explain the materials used in our system. At the core of our solvent is the tannic acid, which acts as a polyphenol ligand. It is naturally abundant, low cost, and contains multiple phenolic groups that can coordinate strongly with metal ions. We combine this with an iron salt, which is the FeNO3 thrice, which forms a metal polyphenol coordination network. The Fe3 plus ions act as an active metal centers and help create adsorption sites for CO2. To improve the stability of the metal centers, we also introduce ascorbic acid or vitamin C, which acts as a stabilizing and reducing agent and helps mitigate unwanted oxidative reactions in the system. Sodium silicate is used as a binder to improve the mechanical strength and structural integrity of the solvent. The active solvent is supported on carbon pellets, which provide high surface area and good gas permeability, making them suitable for a pack for this system. To control the humidity conditions inside the system, we include a dehumidifying chamber filled with silica gel, which removes excess moisture and allows better regulation. For regeneration, we use a PTC heat fan, which provides controlled heat and airflow for efficient desorption of CO2 from the solvent. Overall, all the materials that are selected ensure low cost, availability, stability, and compatibility with the modular carbon capture system.
The developed model is a compact direct air capture unit designed for efficient CO2 adsorption under controlled conditions. Ambient air enters through an inlet pipeline connected to a dehumidification unit packed with silica gel, which reduces the relative humidity to below 20%. The dehumidified air then flows into a vertical reactor column containing a radial axial flow packed bed. It consists of carbon pellets functionalized with tannic acid ferric metal phenolic network, which enhances CO2 adsorption through combined physical and chemical interactions with active phenolic sites. The radial axial configuration improves gas-solid contact, ensures uniform flow distribution, and performs efficiently across a wide range of flow rates compared to conventional beds. Treated air exits through an outlet with reduced CO2 concentration. For regeneration, the system can be extended to a dual reactor setup operating on a temperature adsorption swing principle, where heaters and hot air dissolve CO2, producing a concentrated stream that can be directed to storage for carbon capture and utilization applications. The model contains of an inlet which is connected to the dehumidifier. The dehumidifier is connected to the reactor through a centrifugal fan. The reactor, shown by the yellow cylinder, has an outlet which gives out air devoid of carbon dioxide.
Moving on to the mechanism behind the carbon capture. At the core of our system, we have the thin iron tannic acid metal polyphenolic network, which is the main adsorbent to capture the CO2. To increase the structural stability of this network, we coat it onto an activated carbon pellet layer, which provides high surface area, enabling the CO2 to diffuse efficiently through its pores and maximizing its contact with the active sites. In further, we incorporate two more additives into this system. First, we have sodium silicate, which introduces selenol groups and creates a mildly alkaline environment, improving the interaction with the acidic CO2 molecules. Second, we have ascorbic acid or vitamin C, which stabilizes the Fe plus 3 centers and controls the chelation process, ensuring that the coating remains thin. It also acts as a preventative antioxidant, preventing the OH free radicals from reducing the Fe plus 3 centers. Now, during the adsorption process, there are two mechanisms that occur simultaneously. Initially, the CO2 undergoes physisorption within the porous carbon and the metal network. The weak van der Waals forces hold on to the CO2 molecules, slowing them down, increasing their residence time within the adsorbent. Following this, the chemisorption process takes place where the CO2 molecules interact with the phenolic hydroxyl groups through hydrogen bonding. At the same time, the Fe plus 3 centers act as Lewis acid sites, polarizing the CO2 molecule and strengthening its interaction with the surface. Additionally, in the presence of trace moisture, like relative humidity below 20%, the mildly alkaline environment promotes the formation of bicarbonate ions, enabling the reversible capture of CO2. This combination of physical and chemical interaction significantly improves the capture capacity and the selectivity of the system towards CO2. Once the material reaches saturation, we can move on to regeneration, which is achieved using a temperature swing adsorption mechanism where the adsorbent is heated to up to 60 to 80 degrees to break the weak interactive bonds and release the CO2.
Now, I'll discuss the SWOT analysis of our system. So, one of our key strengths is that this is a relatively new process, which opens opportunities for further optimization and innovation. The system uses abundant raw materials such as tannic acid and iron salts, which reduce overall material costs. This also results in a low-cost sorbent system, making the technology potentially accessible and potentially more accessible compared to conventional DSC materials. Additionally, the design is simple and modular, meaning multiple units can be easily scaled. One challenge in the formation of hydroxyl uh, free radicals due to Fenton-like reactions involving iron, which can potentially lead to solvent degradation over time. Another limitation is that if the incoming air is highly basic, it may react with the iron coordination centers and affect the solvent stability. Our system aligns well with the concept of a circular economy, where captured CO2 can be used in various industrial processes, and as well as the tannic acid from tanneries or other industrial wastes can be used in our system. The modular design also makes the technology scalable, allowing deployment from small units to large installations. Another opportunity is the use of industrial waste heat for solvent regeneration, which can significantly reduce energy requirements. Finally, the system can potentially be integrated with renewable energy sources, making the process more sustainable. Some threats, like potential contaminants in air streams, could reduce the solvent efficiency or shorten its lifetime. There's also competition from structured DSA systems that already exist at larger industrial scales. Finally, like most adsorption-based systems, long-term solvent degradation remains a challenge that needs to be addressed through material optimization.
Moving on with the safety considerations of our system, we have divided our safety considerations into two categories, starting with the chemical safety. All standard chemical handling protocols are followed during preparation and operation. in addition to several specific precautions relevant to our system. First, all the chemicals used in our process are non-hazardous and comply with OSHA and EPA restrictions, ensuring that no regulated or highly hazardous substances are involved. However, iron 3 plus solutions are corrosive, which means they can potentially damage surfaces or equipment. To address this, all solution preparation is carried out in chemical resistant containers to prevent corrosion and ensure safe handling. Additionally, iron 3 plus solutions may cause skin and eye irritation upon contact. So, all handling is performed using proper PPE such as gloves, lab coats, and safety goggles. Another important consideration is temperature control. Excessive heat may degrade the tannic acid coordination network, which would reduce the sorbent's performance. Therefore, the system operates under controlled temperature conditions. Finally, under normal operating conditions, there are no side reactions or byproducts formed, ensuring chemical stability and minimizing unexpected reaction hazards. Moving on to the system safety, first, all mechanical components are properly insulated and secured using reliable container connectors to prevent electrical hazards such as short circuits. Second, any moving components such as pumps or valves are properly shielded to eliminate pinch points and prevent accidental contact upon operation. Thermal safety is also considered as overheating of system components may pose thermal hazards. So the system is designed to operate under controlled conditions. From a structural perspective, all components are firmly mounted within the system frame, preventing displacement or instability during operation. Additionally, pressure buildup within the system could create operational risk, so the system operates close to ambient pressure conditions to minimize this hazard. Finally, all tubing and connections use tight fittings and sealed joints, which helps prevent leaks and ensure safe operation of the system. Now moving on to the unique selling points of a solution. Our system is based on a bio-derived metal polyphenol sorbent, where tannic acid, a naturally abundant plant polyphenol, is cross-linked with iron 3 plus ions. The synthesis is performed in water, making the material environmentally friendly and sustainable. This approach provides a sustainable alternative to conventional amine-based carbon capture systems, which often suffer from volatility, oxidative degradation, and high energy requirements. The capture mechanism itself is also distinctive. CO2 adsorption occurs through quadruple dipole interactions with phenolic groups and Lewis acid polarization from iron 3 plus metal centers. This creates a novel metal assisted adsorption pathway that is both strong and reversible. Another advantage is low temperature regeneration, which reduces energy consumption, one of the major cost barriers in direct air capture technologies. Additionally, the reversible interaction between CO2 molecules and metal phenolic sites allows fast adsorption-desorption cycling, enabling efficient continuous operation. The materials used, such as tannic acid, ferric salts, and other supports, are widely available and inexpensive, making the sorbent system scalable and economically viable for large-scale deployment. Finally, this process follows the circular economy principle, where tannic acid, a waste product in many industries, is used as a raw material.
Right now, industries need carbon removal solutions, but most existing systems add significant costs and energy demand, which limits real world adoption. At the same time, there is a large amount of tannin rich biomass, like tree bark and agro waste, that is being underutilized, along with industries that already produce tannic acid as a byproduct. So these can be utilized as potential sources for our adsorbent. Our model connects these gaps. We convert these low value resources into a functional CO2 capture system that can integrate directly with industries, especially those that already generate waste heat and CO2 rich streams. Because our system operates with low energy requirements and enables fast desorption cycle. It can capture CO2 more efficiently over time without adding heavy operational burden. This makes our solution not technically viable but also practically adaptable at scale. Now, moving on to the budget. Our electronics add up to $190.5, and the framework used adds up to $82.39, and the chemicals used add up to $94.67, and And coming on to miscellaneous and mechanical equipment, they add up to $104.92, with a total adding up to $536.6.
To conclude, our project presents a novel direct air capture system that combines material innovation with an efficient process design. I would like to mention that for this project, we exclusively focus on the CO2 capture mechanism. Regeneration is mentioned only as a potential future extension. We developed a bio-derived solvent using tannic acid, Fe3 plus metal polyphenol network, supported on porous carbon. This material enables effective CO2 capture through mechanisms such as quadruple dipole interactions and metal-assisted polarization, even under controlled humidity conditions. The system operates using a dual bed adsorption regeneration cycle, where one bed captures CO2 while the other undergoes regeneration through a temperature swing process. This ensures a continuous operation with relatively low energy input. From a design perspective, the system is modular, simple, and cost effective, using abundant and inexpensive materials. It also aligns with circular economy principles, as it can utilize tannin-rich biomass and even low-grade industrial waste heat for regeneration. We also analyze the system using through SWOT, highlighting the strengths like scalability, sustainability, while acknowledging challenges such as solvent degradation and sensitivity to contaminated air streams. In terms of safety, both chemical and system level precautions have been incorporated to ensure stable and reliable operation. Overall, with further optimization and integrated with renewable energy or industrial processes, this system has a strong potential for scalable and sustainable carbon removal. Thank you.